So yeah, at least the projector is working for my computer right now. Okay, so the paper I'm presenting is called "Yesterday My Program Worked, Today It Does Not. Why?" This is by Andreas Zeller, who's now a professor at Saarland University in Germany. So now this is a very unconventional title, as I think we've all noticed. It doesn't really talk about the contributions or what their solution is about. Like, you could just call this delta debugging, a technique for whatever. But it does quite nicely sum up the motivation and the situation that we're trying to resolve. And it did catch my attention. And when I read the paper, the very first line of the paper was, "The GDB people have done it again." And this is a very dramatic and unconventional opening, but it did its job. It got me interested. And I thought the rest of the paper was quite well written. It explained the situation. The algorithm was pretty cool, and I thought it was explained quite well. And this idea, as Frank said, has been quite popular, and there's been quite a bit of impact there. This was the first in a series of papers about this delta debugging technique and different applications of delta debugging. In 2009, Andre Zeller won the Impact Paper Award for this work, and he was asked to deliver a keynote. The slides are online, but not the video. It's corrupt, apparently. And there's been over 100 citations of this paper, and the most recent citation was just this summer, so people are still interested in citing this paper, and it's still relevant today. So this is the situation we have, and I've made up this fake Git log. We're starting at yesterday, and at some point it's working, our program is working, and then let's say that overnight people have been working on our project, and now today when I merge in pull request 64, everything is broken, and I don't know why. So there is a tool in Git that lets us bisect. It's called Git bisect, and it lets us choose, using binary search, lets us find which commit has the problem. But that leaves us with the situation where we've got this big commit which has changed over 100 files and made like 9,000 lines of code have been changed in. We still need to identify which of these specific changes introduced the bug. And this is a lot to work with, and it'd be really nice if we could do this automatically. And that's what delta debugging gives us. So to start, we need a set of changes, C, and we call a change set a configuration. And the empty configuration is called the baseline, and that's yesterday. That's everything that we know is working. For delta debugging, we also need a test function, and this test function takes a subset of the possible changes, and there are three possible results. Either it passes, so the bug is not observed; it fails, the bug that we care about has been triggered by this set of changes, or it's unresolved. We don't know whether the test has passed or failed. Maybe we can't even build our program, and maybe it did run and it did build, but something else happened and we don't know what the result is. And throughout this, our assumption is that yesterday, when we apply the baseline, our program works, but today, when we apply all our changes, it doesn't work. And I should clarify at this point that I'm talking about specific changes, specific lines of code that have been changed and not commits. So maybe you changed a signature, a function signature. That would be an example of one change. My cursor is gone. Okay, and our goal is to find the minimal failure-inducing change set. And we say if change set is failure-inducing, let's say C prime. So if we consider all subsets of, so if we say C is failure-inducing, if all supersets of C, we'll call them C prime, are not passing. So this means you have some set of changes, and if you add more changes to it, it's not going to start working again. And by definition, our set of all changes, big C, is failure-inducing, but that's not really helpful. I mean, we already know that. We want to find the minimal set. We find some set where if you take a subset of that, it's not going to fail anymore. Now, there's 2 to the n possible subsets here if we say that there are n changes, and there's no relation between them. Searching through this, we could just use exhaustive search, but that's really expensive. So we want to take advantage of some useful properties which can help us speed up this search. And the first one is if our configuration is monotone. And what that means is if we have a configuration C that fails, and we take a superset C prime, it should not work. So you have some set of changes, and I add another change to it. This new change I add to it should not fix our bug. It should continue to fail. And the converse of that is if we have some set C and it passes, and then I remove a change from it, it should not fail again. And this makes it a lot easier to search for our configurations. We'd also like our configuration to be unambiguous. And this just means that there's only one single cause of our failure. If you have two different configurations that cause an error, they should be, these two configurations and this error should be related. We don't have separate configurations and separate errors. And the last one, which doesn't really happen in practice, but it's something that we really, really would like to have, is if our tests are consistent. You can apply any subset of your configurations and changes, and it will actually give you some deterministic result. It's going to either pass or fail. We don't really like this unresolved question mark here. All right, so let's assume that all three of these are true. And this gives us our first version of the delta debugging algorithm, which I've reproduced from the paper. So we're going to start with some set of configuration C. We'll divide it into C1 and C2. These need to, when taken together, we have to get C back. They have to be disjoint. They're approximately the same size. So now, in our first case, if C contains only one change, this is our base case, then it's failure inducing by default. We're done, we return it, everything's good. In the recursive case, if C1, so for now just ignore this part, if we test C1 and it fails, we can just recurse and search within C1 to find the exact set of changes that cause a failure. And likewise for C2. Now this is an interesting case here. If both C1 and C2 pass, this means that there's some combination of changes in C1 and C2, which only when combined causes a failure. And we want to try to isolate that. And to do that, we have to make two recursive calls. We're going to search within C1, and we're going to pass C2 and R. So this is going to be some set of changes which we keep around. And we're going to fix it, and we're not going to make it any smaller. We're going to keep it around and hope that once we found something in C1, we know that whatever change we find in C1 combined with something in C2 will cause a failure. And if we repeat our search the other way around, searching within C2 and fixing C1, then we can get some changes within C1 and some changes within C2, which when we combine give us our minimal failure-reducing change set. And the invariant for a recursion is that this R, which we're keeping around and just holding on to, should always pass. But when we combine it with C, which is where we're looking for our actual failures, that should fail. So here's an example that should hopefully clear that up a little bit. So we're going to start with 8 changes, 1 through 8. And we have to test. So we divide it into 1, 2, 3, 4, and 5, 6, 7, 8, and we test. Both of them succeed, which means we have interference, our interesting case here. So now we have to make 2 recursive calls. We want to search within 1, 2, 3, 4, but we keep 5, 6, 7, 8 fixed. And in this other recursive call, we just flip it around and do the same. So let's do our search. We make our call here. We just search 1, 2, and 3, 4. That's how we're splitting 1, 2, 3, 4. And we're keeping 5, 6, 7, 8 fixed. And we have a failure here. So now we can recurse on 3 and 4. And we test again. We see 3 is a failure. Since 3 is only size 1, that is part of our failure-inducing change set. So we return 3. Now we can go back to our other recursive call. And we do the same thing. We find that 5 and 6 fail. So we call within 5 and 6. And now we see that 5 passes. So by process of elimination, 6 should fail. I just left out the case there. And that gives us 6 as the other part that fails. And when we combine the 2, we get 3 and 6. So these are the 2 changes which combined together cause the failure. So that assumes that we have this monotonicity, unambiguity, and consistency properties to hold. But that's not always true. So these 2 at least, we can handle pretty easily. So if you have a configuration that's not monotone, what that means is you have some configuration which causes a failure, and you add some new configuration to it. Now that's going to fix a failure. So what does this mean? So it means that we had something that was broken, you add a change, it's fixed, but at today's configuration, which is where you add all changes, it's broken. So somewhere in between, there's another failure or something that undoes the fixing change. So we do know that there is a failure, and this algorithm will find it. So we'll find one of these 2 failures, and that's good enough for us. If our configuration is ambiguous, that means there's maybe 2 possible failure-inducing change sets. And this is also very easy to handle. We use delta debugging. We're going to find one of the failures. We can fix it, apply our fixes, run the algorithm again, and then fix the other failure. So that's nice. What's not so nice is inconsistency, where you can't determine the outcome of a test. And this seems to be very common. When I was reading the paper, this was the first question I had. It seems unnatural that you could just take your whole change set and apply one line of code, you change a signature somewhere, but not change a function call, and there's no way that's going to work, and indeed, it can't work. So our algorithm needs to account for this. And the idea is we split C into smaller subsets. So before, we would split C into 2 subsets, and that's a very big change from, say, yesterday or today. We know that yesterday the configuration is consistent. It works, and it compiles, and we can get a test result. We know that today is also consistent. It runs, if you get a failure, but we can get that deterministic result. So by splitting C into smaller subsets, we hope to find some configuration that's closer to yesterday, where we add a very small subset to yesterday to the baseline, or we get a configuration that's close to today, where we take all of the configurations and remove maybe 1 or 2 changes. And that, by being closer to known consistent configurations, we hope to increase the likelihood that this new configuration is also consistent. So I'm not reproducing the actual algorithm here because I found that it's quite overwhelming. There's a lot of details that you need to consider, and they also throw in an optimization. And I think that even the formalization makes it a little messier. So I just want to highlight the big differences here and get the big picture across. So the first step to generalizing this algorithm is that we need to now consider n subsets instead of just 2. Before, we would test C1 and C2, but now we have Ci, and we also want to test Ci complement. So in the case of n equals 2, this is just like our first version of the algorithm, except that we have twice as many tests. We have to test C1, C1 complement, which happens to be C2, and then we test C2 again, and then C2 complement, which is equal to C1. There's 4 cases to consider. Found is just as before. If we test Ci and it fails, we know that the failure is within Ci, so we can recurse within Ci and throw everything else out. Interference is also from before. We test Ci, it succeeds. We test Ci complement, it also succeeds. There's some combination, so we have to make our 2 recursive calls, where we call to Ci with keeping Ci complement fixed, and then we search in Ci complement, keeping Ci fixed. So that's just the same as before. But now, because of inconsistency, we have this new case to consider where Ci is unresolved, but Ci complement passes. So we know that the bug cannot be within Ci complement. It has to be within Ci. And we know that in order to make this compile and work, we need maybe some changes within Ci complement to make this possible. So we make 1 recursive call by searching within Ci, but we keep Ci complement around. This is sort of like interference, except instead of making 2 recursive calls, we only make 1. That's why we say we prefer Ci. Now, if none of these cases hold, then we're out of luck. All we can do is just try again, but increase the number of subsets and hope that we get something that's closer to a known consistent configuration. Sorry. And the important thing to note is that the resulting set may not be minimal. But we do know that it is much smaller than before. So that at least is some hope. So here's a quick example of the preference. So let's say we've got, again, 8 changes, 1, 2, 3, 4, 5, 6, 7, 8. Okay, both of them are unresolved, so we have to try again. We'll try 4 subsets now. So we have 1, 2, 3, 4, 5, 6, 7, 8. Now we would hope that one of these ends up as being a fail, in which case we can just recurse and it's easy. But that's not the case. So we have to test the complements. And we would hope that one of these succeeds so that we get into one of our previous cases. But instead, we just get unresolved and error. So this isn't too helpful. We would have to try again. But the optimization pointed out here is that 5, 6 we know for sure passes, and its complement for sure fails. So in all subsequent tests, we don't need to search within 5, 6. We can just keep it around. We just only care about 1, 2, 3, 4, and 7, 8. So that's what we do. We check our 6 changes here, keeping 5, 6 constant. So you can see it's fixed here, but we have 6 cases here, and then we finally find that it's 8. Okay, so as I said before, inconsistency seems like it'll be a big problem, and it is. And in their paper, they actually discuss 2 approaches to managing this. And the first is the obvious, let's just group related changes. Obviously, if you change some function, you want to change its function call. You want to change all the call sites. So we can group changes by time. Maybe they're all made on the same day. File or directory, identifiers, so the function that's modified. And this keeps things related together so that when you choose one change, you have to make all the other changes that are along with it. And the other approach they outlined is called predicting test outcomes. So if you're pretty sure that a test is going to be unresolved, just assume it's unresolved and continue your algorithm. Don't bother running it. And the way you use this is if you can apply a total order to all of your changes and require that if a later change is selected, all previous changes must also be included, otherwise it will fail. And this makes sense if you're ordering these by time. You obviously, if you're missing some of the previous changes, then it's probably likely that it's required and it's not going to succeed. So they did that in their case study with GDB. They ran GDB, there was a bug. Without any of these tricks, they found that it took 470 tests in 48 hours, which is a long time, but at least it was done automatically. But they managed to cut that by more than half by grouping all the changes by file and directory. And they also created this feedback loop where if they applied changes and they tried building GDB and it didn't build, they would scan the error logs for identifiers and then try to apply all the changes that would affect and try to hopefully fix those errors. So this ended up speeding up their process, so that was pretty cool. All right, so related work. So there's been a lot of other work, papers that Andreas Zeller has published related to this. So far, all this work has been using delta debugging to isolate changes to code that create bugs. But another nice thing you can do is you can reduce input. Let's say you've got a test input. Maybe you're debugging a compiler and you have some C program and you've caused some seg fault in the compiler. And the C program is like 10,000 lines long. Well, if you can use delta debugging, you can maybe minimize it and shrink it and get only the interesting bits of your file. Another paper they had was trying to debug concurrent programs. So you've got, this was used in conjunction with the Deja Vu tool, which is able to record and replay thread schedules. So you have a thread schedule that works yesterday, and you have a thread schedule that doesn't work, that's today. And by changing the different scheduling, you can try to find the exact cause of this concurrency bug. And the third item I have here that they wrote a paper on is isolating cause-effect chains. So if you consider a program to be a sequence of program states where variables have certain values and at each execution the state changes, you can consider that as a long sequence. And you know that at some point everything is fine, there's no bug in your program, but at another point, at some other program state, there is a bug. And if you use delta debugging to maybe narrow down and find exactly where in your program this change occurred and exactly which variables are relevant to your bug. And in I didn't read the paper in too much detail, but the related work said this was very similar to program slicing, but they claim that this is much more precise. I can't tell you that because I didn't read the paper, but yeah. All right, so there are lots of implementations of delta debugging. Andreas Zeller's research group has a bunch of Eclipse plugins, which do the minimizing changes, minimizing inputs, and minimizing program state. His group also has an implementation in Python, so you can write your test framework in Python and run delta debugging. There are other tools which are based on the algorithm, based on the delta debugging algorithm. I'm not sure if they use the exact same algorithm, but delta and creduce are for minimizing test inputs, and they've been used to debug compilers. Lithium has been used to reduce JavaScript and XML, and it has been used to debug Firefox. Walla, the analysis tool is from IBM Research. They have a tool, JS Delta, which does the same for JavaScript files to debug any JavaScript front end. And then, of course, dog fooding and things that I've worked on. Flix also has a Delta debugging tool. And since there's time, I think I'll show a demo. Okay, so I'm running this program. I'm running Flix on some input. SUOP is the analysis file, and 256bzip is the inputs for it. And there's some integrity constraints, some assert has failed. So now I'm going to run Delta debugging. And now it's said, okay, there's an error. Now let's try throwing out these different subsets of changes of their input. Let's see how many we can get rid of. And it runs, and it's finally finished. And we've narrowed down 5,000 facts down to 23. And now I've written the file, it's written all those to alt.flix, and if I run it again, it fails, and if you observe, this was much quicker than before. So we've shrunk this down to 0.5% of its original. All right, so conclusions. So delta debugging is a technique for automatically reducing changes to find the exact failure of these changes. And if you have domain knowledge about these changes, for example, when they were made, if you can group them by file, by functions changed, this can really help with inconsistencies. And the cool thing about delta debugging is that it's not, even though the original paper was about changes to code, you can apply it for other things. For example, minimizing test input seems to be one of the more popular applications. And there are lots of interesting implementations of tools that can do exactly this. All right, so discussion questions. So the first is kind of a combative question I have. My observation was that there are all these implementations of delta debugging, but only like 2 or 3 of them, only the ones by Andres Zeller's group, were for actually finding changes. Most of these were for reducing test input. And my intuition from working with software in various internships and research was that inconsistencies seem to be very, very common. If I make a file, if I make a commit to, say, some source code, I try to keep my changes minimal, but I end up changing like tens of files, and I have like hundreds of lines changed. And if I ignore, just omit one of those changes, the whole thing is unresolved. So my intuition, at least, is that inconsistencies are really, really common and a huge problem. And even the solution they devised for their case study seemed very ad hoc. Like they're like, oh, we have this loop which looks at error messages and fixes things, and I'm not convinced that is broadly applicable, at least not without a lot of hacking. So what do people think? Like, is delta debugging something you would use for test input or changes, or like, I don't know. Yep.
Well, I know I was seeing a paper to research for this. I saw a paper that was the title was basically like, is delta debugging useful? It was basically like, are these like debugging tools that academics are coming out with, are they useful? And delta debugging was one of them. So I definitely think there are people who question it, and I don't know if anybody who uses such a system in industry, maybe have you known anyone that uses
like, this is the other thing. Like, I've definitely seen and heard of C-reduce before, and then someone else implemented delta debugging into Flix, so that was cool. But actually using delta debugging to minimize changes was something that I'd never heard of before or seen before.
I guess it kind of felt like the minimal change set didn't necessarily seem like it solved your problems. Because if you're trying to debug your own code, then you just have kind of bad software practices. If you've got somebody wrote something you never fix.
Yeah, so the assumption is you don't test often enough.
Right, like, and so it seems like it's a tool that solves a problem, but it might be better to just avoid the problem entirely, like continuous integration kind of gets
Sure,
you.
but then tests aren't foolproof. I mean, this is more of a, it's broken, like, all right, it'd be great if it wasn't broken, but this is the state it currently is in. Like, I mean, I agree, like, it'd be great if we could stop these early, but sometimes you can't.
Right, well, it seemed kind of like, I guess maybe I didn't understand their GDB example exactly. Like I felt like, did somebody change something in GDB and their plugin to GDB, or their like thing that were live in GDB libraries no longer worked because of some change that had been made? And it seems like sort of, that's the GDB folks, broke the interface or something, or changed the.
I think the scenario was that he we had built some visual debugging tool on top of GDB, and that was broken.
Okay.
Well, there were two scenarios. So actually, Andres Zeller is the main creator behind DDD, which is probably the more popular front end, graphical front end for GDB. And in one case study, DDD, his software was broken. The GDB case study, which we were talking about, was where DDD requires GDB as its backend, obviously,
right.
and then it requires on some textual interface, and GDB changed it, and DDD assumed the previous interface. And well, you could argue that maybe DDD should change to match GDB, but I mean, it's an interface problem.
Right. It didn't seem like it was going to work very well for like refactors and stuff. Once you refactor your code, you end up in like inconsistency hell.
Yeah, like I mean, also in their case studies, they narrowed it down to exactly one line of code, which I guess is the trivial case. But what if you had like a whole bunch of lines that all contributed to your bug? Then like you refactor a function, and that changes hundreds of lines, and all of that is part of your bug. Well, okay, hundreds of lines have changed. Well, now what?
So I have a question. So if I apply one patch and that causes a bug, what is it classified as? That would not have occurred on it, just because I applied this single patch out of the big set, that causes my software to crash.
So do you mean crash or trigger the bug?
Crash.
That's unresolved. Because
How do they know it's unresolved? What does?
So unresolved means was the bug in question triggered or was it not triggered?
And how do they know it's the bug in question?
Yeah, if you have.
Well, if it could be failing in the same place, or.
Then you don't know.
Yeah. Okay.
On that topic, I've been wondering if it would make sense to build some version of this that knows about syntactic dependencies in programs, so that if you change a function, you wouldn't try to apply a change that doesn't also reflect in all the call sites that invoke that function. But I think that would mostly be an efficiency issue, right? It would just avoid exploring all kinds of combinations that wouldn't make any sense.
I mean, I think even in the introduction to the paper, they said in most cases it's faster and easier to just do it manually. It's just that Delta debugging does automatically. So.
Yeah.
Well, don't they sort of? I think it ends in C, and so it's a type language. So wouldn't the type checker sort of throw out the bad cases mostly for you? And you could just say, well, didn't type check, time to bail out, and you move on to the next one after finding inconsistent.
But you could burn up a lot of cycles in running a full-fledged type checker on a program if you could build it into the analysis itself and probably speed things up. Right?
I guess that's the other thing. Like right now, Delta debugging is language agnostic, and it's applicable to whatever. As long as you have some changes and a test function, it works. But the moment you try to like use syntax or like narrow down and group these things, now it's language specific, and yeah. And then my other question is just an open-ended. I don't know the answer to this. What else can you use Delta debugging for?
Maybe one thing which might be quite interesting is to be able to reduce the change in between environments, right? So you can have continuous integration, and all the tests are passing. That's perfect. But suddenly you deploy it in production and it doesn't work because there has been some change in the production, which causes something not to work. The environment variable configuration in database or something like that. And that's really hard to kind of figure out exactly why that happens. It would be really cool if someone came up with some sort of way how to describe all that and then go through this change set and minimize the set of changes which cause things to fail.
So back in the summer, when I was doing my internship at Manford's, they had, I don't know whether they used Delta debugging there, but we had a single node in the cluster where we could deploy our changes, and then it would run the entire integration test and find out if something failed. So only after your change set is complete, you can push it in the node and then run and check whether it works or not. And at that point, say 5 developers pushed their changes and now it's time to run the integration test. You will know whose change set caused the failure in the integration suite, and there was some kind of automatic tool which would tell us that this is a change set number which caused this problem. And when I was reading that, seemed something like what they were doing there.
Like, sort of going back to the first question, I wonder if there's actual like research that's, I'm sure there's research that's been done about how much like programmers tend to use just in general any sort of debugging tools. Like, I mean, I look around and think of my peers and I know I'm guilty of this as well. Just not using a debugger.
The best debugging tool is just baseline.
Yeah, well, it's probably the most common debugging tool, but you know, like this is a pretty heavyweight technique. So the question is like, what percentage of people are even trying something? Like a debugger is probably the most basic debugging tool you have.
So I think this is very, very useful in one specific scenario, that's input minimization. If you have a compiler or so, someone tells you it loads up on this huge program, you need to be able to narrow the input down to a much smaller 10-line program on which things still blow up in the same way. It's extremely useful. That's why the Delta debugger for Wala was built. It was actually to debug a program analysis for JavaScript by enabling it to automatically, if something went wrong, to narrow it down to something much smaller. So for change management like this, I think it's less compelling, but this was the first paper, so that's why I picked it. I think the other paper on input minimization is probably more well cited than this one, although this is probably the most impactful one of the whole thing because it's the
It's
first
the
one.
first one, yeah, and it's the same